Hello, Professor. This is Asith Vasireddy from Theory of Computation class, and my netted is KQ6053. I'm here to present a topic which is Turing machines. A Turing machine is an accepting device which accepts the languages generated by type 0 grammars. It was invented in 1936 by Alan Turing. It is also a simple mathematical model of a computer, modeling the computing capability of a computer. A Turing machine is a mathematical model which consists of an infinite length tape divided into cells on which input is given. It consists of a head which reads the input tape, a state register stores the state of the Turing machine, and after reading an input symbol, it is replaced with another symbol. Its internal state is changed and it moves from one cell to the right or left. If the Turing machine reaches the final state, the input string is accepted, otherwise rejected. It normally accepts the input string or completes its computation by entering a final or accepting state. Tape is used for input and working storage. A Turing machine can be formally described as a seven tuple, where Q is a finite set of states, X is the tape alphabet, sigma is the input alphabet, delta is a transition function, Q naught is the initial state, B is the blank symbol, F is the set of final states. Here you can see the diagram of the Turing machine model, where it contains the raw head, finite control, and the tape, which is divided into cells and of infinite length. Transition function. Transition function is denoted by delta of q and x, where q is the current state and x is the current tape symbol. And we have different variations of Turing machines, which are multi-tape Turing machines, non-deterministic Turing machines, multi-head Turing machines, offline Turing machines, multi-dimensional Turing machines. Multi-tape Turing machines. Uh, this is the Turing machine with several tapes, and every tape have their controlled own head. For n tapes, Turing machine M is equal to, here we have the formula, Q dot E R 5.90 BF. You can refer to the 7 tuples. Non-deterministic Turing machines. It is similar to deterministic Turing machines, except that for an input symbol and current state, it has a number of choices. A string is accepted by a non-deterministic Turing machine if there is a sequence of moves that leads to a final state. The transaction function 8 is QXT. Multi-head Turing machines. Multi-head Turing machine has a number of heads instead of one. Each head independently read or write symbols and move left or right or keep stationary. Offline Turing machine. An offline Turing machine has two tapes. One tape is read only and contains the input, whereas the other is read write and is initially blank. Here you can see the diagram as the read only input files tape and write or read tape is connected to the control unit. Multi-dimensional Turing machines. A multi-dimensional Turing machine has a multi-dimensional tape. For example, a two-dimensional Turing machine would read and write on an infinite plane divided into squares like a checkerboard. For a two-dimensional Turing machine transaction function defined as QXT. And let us now see a sample problem of the Turing machine. Here the program tells that machine what tasks to perform for every Turing machine. Every Turing machine must have a start or initial state, and the current cell of the strip of the machine will determine its next by indicating an arrow called a state transition. The machine will also change the value in the current cell and may move the head to the left or right or keep it in the same place. So in the initial state, we see that the current cell has value 1, and a state diagram tells us that we will transition to state Q1, which change the value of the current cell to a 0 and then move the head to the left. The other cell, now, now we are in state Q1 and our current cell has value 0. The state diagram tells us to transition to state Q2 and then changes the current cell to 1 and keep the head in the same place. Now we are in the Q2 state and our current cell has value 1, and the state diagram tells us to transition back to our initial state, which changes the current cell value to 1, which it already is, and move the head to the right. Finally, since our state is the initial state and our current cell's value is 0, we transition to the halting state and change the value in the cell to 0 and keep the head in the same place the halt state is. Another critical state that every Turing machine needs without the halting state is that the machine will keep looping forever and never complete its programmed tasks. Finally, let us talk about the applications of Turing machine. Check decidability is one of the application. If the Turing machine cannot solve a problem in countable time, then there could not be any algorithm which could solve that problem, which is undecidable. For a decision problem, if its Turing machine halt in countable time for all finite length inputs, then we can say that the problem could be solved by an algorithm in countable time. Classify problem. Turing machine helps us to classify decidable problems into classes of polynomial hierarchy. Suppose we found that the problem is decidable, then our target become how efficiently we can solve it. The efficiency being calculated in number of steps, extra space used, length of the code or size of the FSM. Design and implement algorithm for practical machines. Turing machine helps to propagate idea of algorithm in the other practical machines, and after the successful check of 1 and 2 criteria, we can use our practical device or computers to design and implement algorithm. Thank you.